Hello, everyone. My name is Ashley Anderson. I'm with the College of Engineering at Cal Poly Pomona, and my faculty mentor is Dr. Binder. This presentation will be on the spatial correlation of high-mass X-ray binaries and young star clusters in nearby star-forming galaxies. The main question for this research is how are high-mass X-ray binaries and young star clusters related? First, let me explain what each of them are. High-mass X-ray binaries are when a star orbits a black hole or neutron star. While in orbit, the high-mass donor star gives material to the black hole or neutron star. This material accelerates, and when it hits the high-mass object, it emits X-rays, which we can detect. Young star clusters are tightly packed areas where young stars are born. High-mass X-ray binaries and young star clusters are expected to be connected because they are spatially correlated in their host galaxy. Based on previous research, we looked to see if there was a correlation between these two. In the top three images, going from left to right, we have the following galaxies: M31, M33, and NGC 300. You will see red and blue markers. The red markers are high-mass X-ray binary locations, and the catalogs are taken from, while the blue markers are young star clusters and their associated catalogs. The bottom three histogram graphs show a distribution of distances between high-mass X-ray binaries and their nearest neighbors for the three galaxies mentioned before. Distributions of distances compared to randomly distributed high-mass X-ray binary locations within the young star cluster footprint are shown in white. For every single high-mass X-ray binary, we draw a ring, and then count how many young star clusters are in that ring area. Then we draw another ring, and count up how many young star clusters are in that next ring up, and so on. Looking at the spatial correlation function to the right, you will see several variables in the equation. The NDD is the number of observed young star clusters found in each ring. This represents data pairings. The NDR, or data random pairings, follows the same procedure using the true location of each high-mass X-ray binary, but this time using a randomly distributed young star cluster population in each galaxy. The NRR, or random pairings, are randomized locations for both high-mass X-ray binaries and young star clusters in each galaxy. And finally, the R represents 100 parsec thick radial bins. So, how do we interpret xi? At xi equals 0, there is no correlation beyond random. In other words, the probability finding these two sources near each other is exactly equal to the random chance probability. At xi greater than 0, there is a tighter correlation compared to random chance. At xi equal 1, there is 100% excess probability, meaning you are twice as likely to find sources near each other compared to random chance probability. The higher the xi function, the more tightly clustered the populations of young star clusters and high-mass X-ray binaries are. The spatial correlation function for galaxy M31 is shown in black. Galaxy M33 is pink, and NGC 300 is blue. The horizontal dashed line at zeta equals 0 represents the value expected for no spatial correlation. The spatial correlation function for all three galaxies show clear excess at distances about less than 700 parsecs. The M31 black line, the innermost bin, has a xi of about 1. What that means is that you're twice as likely to find a young star cluster near a high-mass X-ray binary compared to random chance. For NGC 300, the peak is at 1.6. So you're 2.6 times as likely to observe these sources close together. And M33 is 4 times as likely. In the innermost bin, the observed clustering xi between high-mass X-ray binaries and young star clusters is greater than 8 sigma, above the value expected for no correlation in all three galaxies. Why do we see those different peak values? Why aren't they all the same? The galaxies have different specific star formation rates, which is linked to the average age of the stars in the galaxy. The peak value of the spatial correlation function xi with r less than 100 parsecs between high mass X-ray binaries and young star clusters as a function of specific star formation rate of the host galaxy. Values for the Milky Way and NGC 4449 are taken from the literature. There is a clear correlation between host galaxy specific star formation rate and the excess probability of finding a high mass X-ray binary within 100 parsecs of a young star cluster. Why did we choose to look at specific star formation rate as opposed to star formation rate? All the galaxies we studied are different sizes. If the galaxies observed were similar in size, we wouldn't need specific star formation rate. Specific star formation rate is important because all of the galaxies observed are substantially different in size. NGC 4449 is a dwarf galaxy, while M31 is 100 times bigger. Specific star formation rate measures how much mass per year is being converted into stars, divided by the mass of the entire galaxy. This allows us to compare apples to apples star formation rates. In other words, comparing the galaxy similarities, not their differences. Star formation rate doesn't reveal how vigorous the galaxy's formation rate is, but specific star formation rate normalizes by galaxy mass. This reveals how vigorously the galaxy is forming new stars. For example, the galaxy NGC 4449 has a high star formation rate and a high specific star formation rate because it is much smaller than all the other galaxies studied. NGC 4449 has a high star formation rate and specific star formation rate because it is much smaller and younger than the other galaxies. Because NGC 4449 is younger, the average age of stellar objects will likely be younger, as opposed to older stellar objects in the mature M31 galaxy. How is this related to the spatial correlation with high mass X-ray binaries? If high mass X-ray binaries experience a kick during an asymmetric supernova during compact object formation, then the separation between a high mass X-ray binary and its birth cluster increases with time since initial compact object formation. We would therefore expect younger high mass X-ray binaries to be located systematically closer to their birth clusters than older high mass X-ray binaries, which matches our findings. Thank you very much.